Hey, geometry students, in this lesson, we are going to be learning how the ratios of areas and perimeters are related when we have similar figures. And actually, in a previous lesson, we already learned how the perimeter ratios are related. That's the first part of theorem 87.1. If two similar figures have a scale factor of a to b. Now, I really strongly prefer to show ratios like this as a divided by b because we can actually do that math and divide one side by the other side. Then the ratio of the perimeters is a divided by b. The same scale factor. We already learned that in a previous lesson that the scale factors of the sides of similar figures are the same as the scale factors of the perimeters. Then the ratio of their areas, okay, which remember to find area, we need to multiply two side lengths together, and maybe something else like in a triangle, we multiply by 1/2. Um, but the ratio of their areas is a squared to b squared, or a squared divided by b squared. And before I said the scale factor is a over b, a squared over b squared is just a over b squared, or the scale factor squared. I want you to think about this for a second. Let's say that square a and square b are similar figures. To convert a to b, I would have to multiply by some scale factor, okay? Now, square a has an area of a squared. How does the area of square B relate? Well, let's think about that. In order to turn A into B, I had to multiply by a scale factor. I had to do that on this side, and then I had to do the same thing. I had to multiply by that same scale factor on this side. Now, when I find the area, I have to multiply this side, which is A times a scale factor, times this side, which is A times a scale factor. Okay, so I get A squared times the scale factor squared because I had to multiply by the scale factor on both sides. And that's what we're going to be dealing with in this lesson. The first thing we need to do is prove that. Okay, so letter A says prove the second part of theorem 87.1. That's proving that the ratio of the scale factors is a squared over b squared. In other words, for these two triangles, I'm proving that the area of triangle PQR divided by the area of triangle WXY equals PR squared over WY squared. We're just going to use this bottom side length as the scale factor. We're comparing this side to this side, and when we divide those two, we get the scale factor between the two similar triangles. All right, so how are we going to do this? Well, I'm going to do this very informally, okay? And the place that I'm going to start is I'm going to say that the scale factor x, okay, we'll say that we have some scale factor. I'm going to call that value x. That's the value we multiply PR by to change it into WY, okay? We're going to say that that scale factor, by the definition of a scale factor, is PR over WY. And the only reason I'm using that PR over WY instead of WY over PR is because that's what I'm trying to prove is in terms of PR over WY. Okay, so the scale factor is PR over WY. Now, the next thing that I'm going to do here is I need to calculate the areas of these triangles. And to find the area, I need to take 1/2 the base times the altitude. But I don't know, I haven't established that these altitudes are similar. Okay, let's think about that for a second. So if this triangle is similar to this triangle, that means that all three angles have to be the same by the definition of similar triangles. Okay, and I'm not going to write that down. I'm just going to note that the interior angles of these triangles all have to be the same. Now we're going to drop an altitude from the top vertex that bisects the top angle for both of these triangles, or at the very least, even if it doesn't bisect the top angle, it's going to be perpendicular to the bottom segment. What's going to happen is you can imagine that because these angles are the same, dropping a vertical is going to do the same thing to both angles. And therefore, this angle here is the same as this angle here. So PQS is the same as WXZ, or SQR would be the same as ZXY. And because I have an angle here that's P and W haven't changed, we know those are still the same angle. And then PQS and WXZ are similar. what or are the same angle. I'm sorry, they're the same angle. We have angle similarity. So I'm going to say by angle similarity, and that's pretty easy to prove. I didn't show every single step of it, but we could prove it. By angle similarity, PQS is similar, and this is triangle PQS. I'm just going to very informally use a triangle symbol that looks like that. We're going to say that that means triangle PQS is similar to triangle WXZ. Okay, that's by angle similarity. Okay, now what's the next thing that we're going to do with this? Um, if I know that these two triangles, these two right triangles are similar, I can say that there's a scale factor x equals PQ over WX, which is the same as PR over WY, because notice that PQ and WX, that scale factor was in the original triangle. And this, because the original triangles were similar, PR and WY were in that original triangle, so they're going to have the same scale factor, which is also equal to the scale factor of QS over XZ. So all of these scale factors have to be the same because these are similar triangles. Similar triangle sides are related by the same scale factor. Okay, so what does that mean? Well, that means that to calculate the area, we need to take 1/2 times the length of PR times the length of QS in the first triangle. 1/2 times PQ times RS equals the area. We're going to say area of triangle PQR equals this. Okay. And then we could also say the area of triangle WXY equals this: 1/2 times WY, I'm sorry, times XZ. Okay, now let's just take a look at what I've got here. PR times QS. But wait a second. I can look at these scale factors and I wonder if there's a way for me to work these scale factors in. If I were to go ahead and divide the area of PQR by the area of WXY. Okay, so I calculated the area one, I calculated the area of the other. What if I did what would happen if I divided them? So I'm going to do the same thing. I'm just going to go ahead and copy this down here. This divided by this. Okay. Now, what I can do is I can cancel out. Let's see. Before, yeah. Okay. So the area of PQR over the area of WXY equals, and I should just put one equal sign here. Let me fix this. So that's the thing that was standing out as a little bit confusing about this. Okay, so there should be one equal sign in between these two fractions. Okay, there we go. And now let's just take a look at this. I can cancel anything that's the same in the top and the bottom. 1/2 over 1/2 cancels out. So I'm left with it equals PR times QS over WX times YZ. I'm sorry, WY times XZ. WY times XZ. But let's look at this for a second here. PR over WY is the scale factor X. QS over XZ is the scale factor X. So I can say that this is actually equal to X times X, which equals X squared. Okay, the scale factor squared. And then since the scale factor is PR over WY, I can prove, okay, so actually I've already proved everything I need to prove, But now, just to make my proof equal this, since x equals, by substitution, x equals PR over WY, we proved that back here. I could say that the area ratio equals PR over WY. I'm just going to substitute that in for x squared. And that is how we prove our theorem 87.1. We proved that the ratio of the areas of these two figures is equal to the scale factor squared.